In this video, I'm going to introduce or reintroduce you to forces and Newton's first law and Newton's second law of motion. First, what is a force? A force is a push or a pull. Forces have both a magnitude and a direction. In other words, we need to know both how strong the force is and in what direction the force is acting. Another way of saying this is that force is a vector. Now let's talk about what we mean by the phrase net force, because this will be a common phrase that we'll be using a lot. So if there is a single force acting on an object, then that single force could also be called the net force. So let's do an example. Let's imagine I have a box sitting on a table, and there's a single force acting on the box. The magnitude of this force is 5 newtons. Newtons are the SI unit for force. And the direction of the force is to the right. So the force is 5 newtons to the right. I'm specifying both its magnitude and its direction. What's the net force on this box? Well, since there's only one force, single force acting on the box, then the net force must be 5 newtons to the right. Let's do another example. Again, we have a box sitting on a table, and this time we have a force pushing to the left with 3 newtons. What's the net force on this box? Again, since there's a single force, the net force is equal to that single force. Okay, so this is very simple so far. If there's a single force, then it's the net force. Now, what if both of these forces that I've drawn here are acting on the same box at the same time? What is the net force now? We can reword this question as follows. Can we find a single force that has the same effect as these two forces combined? If we can find a single force that has the same effect as these two forces, then that single force would be the net force. Can we find a single force that has the same effect as these two forces? This could be figured out experimentally. And if this were a physics lab course, I would actually have you do this experiment. But the answer turns out to be that the net force is 2 newtons to the right. Which means if we examine the motion of a box being subjected to these two forces, 5 newtons to the right and 3 newtons to the left, and compare that to a box being subjected to a single force of 2 newtons to the right, then we'll see that these two boxes have the same motion. These two situations are indistinguishable as far as the motion of the box is concerned. Therefore, then the 2 newtons to the right is the net force. Intuitively, we can think of this as follows. The greater force will win out over the smaller force. So the net force will be to the right because the greater force is to the right. But the smaller force of 3 newtons that's opposing the bigger force of 5 newtons will cancel some of the 5 newton force, leaving 2 newtons left over. So in this case, we've subtracted because they are opposing forces. The word net and net force already hinted at this idea. If you make both a deposit and a withdrawal from your bank account, then the net deposit is the deposit amount minus the withdrawal amount. So when we're talking about net, we already have this idea of subtraction and cancellation. Now, we don't always have cancellation. Sometimes we make 2 deposits. So what if both forces are pushing in the same direction? Again, we can answer this experimentally. And we can find that a single force that has the same effect as these two forces combined would be a force of 8 newtons to the right. So since they're in the same direction, we add them together. Let's do one more case. What is the net force in this case? I have a 5 newton force pushing to the right and another 5 newton force pushing to the left. So they are equal and opposite. And since they are opposing, then we will subtract them. And in this case, the net force then is 0 newtons. In the case of zero, we don't include the direction because zero doesn't have a direction. But this is the only time we would not include a direction when we're talking about forces. In the case of zero net force, we call this balanced forces. And in the case of a non-zero net force, I'll call this unbalanced forces. Okay, and I need to add the word net in there, that's important. So this is what I mean when I'm talking about balanced or unbalanced forces. One thing I'll add is that so far, we've just done forces that are left or right. We haven't done up or down or anything on the diagonal. As soon as we do that, we are getting into two-dimensional motion. And Newton's laws still apply in 2 dimensions. We just have to treat each dimension independently. So we would have to do Newton's laws in the horizontal direction and then Newton's laws in the vertical direction independently, for example. For simplicity now, I'm just going to focus on one-dimensional motion. So far forces are either left or right, or we'll see up or down forces, or east and west forces, or north and south forces, and so on. Now that we know about net forces, we can talk about Newton's first law. This law is very easy to state in terms of net forces. So Newton's first law states that if the net force on an object is zero, then that object does not change speed. If you've seen Newton's first law before, you may have heard it stated slightly differently, such as an object at rest stays at rest and an object in motion stays in motion. But our version is a bit more precise, so we will use this version. Other ways of saying the object doesn't change speed might include it doesn't speed up or slow down, or there's no acceleration or deceleration. And deceleration is sometimes thought of, physicists think of this as negative acceleration. So physicists will use one word to cover both acceleration and deceleration. Acceleration covers both speeding up and slowing down because it includes both positive and negative acceleration. So these are all different ways of saying the same thing. The key is that an object does not change speed when the net force on the object is zero. Notice I've said nothing so far about what speed the object currently has. That's because Newton's first law is true regardless of the current speed of the object. Therefore, it's true whether an object is moving or at rest. And this is the case with all of Newton's laws. Newton's laws are true regardless of the current speed of the object. And therefore, Newton's laws are true regardless of whether the object is moving or at rest. So let's do an example of me sitting in my chair. I'm sitting in my chair and I'm not going anywhere. Is there a non-zero net force acting on me? Well, I'm at rest and I'm staying at rest. Therefore, my speed is not changing. Therefore, the net force on me must be zero. So if I'm at rest and staying at rest, then my speed is not changing. Therefore, the net force on me is zero, according to Newton's first law. But just because I said the net force is zero, does that mean there are no forces acting on me? Are there any forces acting on me right now? The answer is yes. And we'll talk about this more during this week's activity, but the force of gravity is acting on me right now. And if the net force on me is zero, then there must be at least one other force acting on me that balances the force of gravity. So this is a stick figure of me, and the force of gravity is pulling down on me. But since the net force is zero, then there must be some upward force that is balancing the force of gravity. This upward force could be from the floor if I'm standing, it could be from the chair if I'm sitting. So the net force on me is zero, but there are still forces acting on me. Okay, I've already mentioned that Newton's laws are true whether an object is moving or at rest, and I just did an example of an object at rest, me. Now let's talk about the moving case. So imagine a car on a highway that's moving at a constant speed of 60 miles per hour. What is the net force in this case? The key word here for you should be the word constant. If the speed is constant, then it's not changing. In other words, the speed is 60 miles per hour and it's staying 60 miles per hour. Just like when I was in the chair, my speed was 0 and was staying 0. So what's the net force? In this case, it's 0. Because my speed is not changing, or the car's speed is not changing. So this is a very common and frequently misunderstood idea. The car is moving, but the net force on it is 0. Something does not need to have a net force acting on it in order for it to be moving. But are there forces acting on the car? Absolutely. We have gravity. We have the road pushing up against gravity. We have friction between the tire and the road. We have air resistance of the air hitting the windshield in the front of the car. We have the force of the engine pushing it forward. So there's all these forces acting on the car, but all of those things must be balanced if this car is moving at a constant speed. And that's Newton's first law. Okay, now we're ready to move on to Newton's second law. Newton's second law can be summarized as a non-zero net force causes a change in speed. And remember how a physicist says a change in speed, often using the word acceleration. So a non-zero net force causes a acceleration or a change in speed. It can also cause a change in direction. So I'll come back to that later this semester. Among other things, Newton's second law can predict whether something is going to speed up or slow down. So let's address that first. So suppose a non-zero net force acts on an object. So you can see right away from Newton's second law, if a non-zero force is acting on an object, then there's going to be a change in speed. So one question we might ask is, does the speed increase or decrease? Are we going to have negative or positive acceleration? So let's break this into two cases, the case at rest and the case where the object is moving. And remember, Newton's laws work whether the object is moving or at rest. So let's do at rest first. So if an object's at rest, another way of saying that is that its current speed is 0. And if there's a non-zero net force acting on this object, its speed must change. Its current speed is 0, so the only way that its speed can change is to increase. So the net force, the non-zero net force, causes the object to speed up. Now, what if the object was already moving? In this case, we're going to break it down into a further two cases. And those cases will depend on the direction of the net force and the direction of the velocity currently. By the way, I use the word velocity there. Velocity is the word for speed that also includes the direction of motion. So velocity is a vector. It has a magnitude and a direction. The magnitude of the velocity is what we call speed. Or to put that another way, velocity is speed plus direction of motion. So our first case will be the case where the net force and the direction of motion are the same. The only other case we can have in one dimension is that they are opposite. Since we're in one dimension, everything is acting along a line. So two arrows that are along the same line can either be pointing in the same direction or they must be pointing in opposite directions. So the first case we'll do is where the net force and the direction of motion are the same. In this case, the object will speed up. For instance, say something is moving to the right and you give it an extra push that's also to the right. That will cause it to speed up. As I mentioned, the only other case that we have to consider in one dimension then is what if the net force and the direction of motion are in opposite directions? And in that case, the object will slow down. For instance, something could be moving to the right and you start pushing it on it to the left. And that will cause it to slow down. So let's return to the car on the highway example. So let's take our car that was going 60 miles per hour and suppose it speeds up from 60 to 75 miles per hour. While it's speeding up, was there a net force on the car? Well, if its speed was changing, then Newton's second law tells us there must be a net force acting on the car. So just to be extra clear, Newton's second law is telling us that there's a change in speed if and only if there's a non-zero net force. Once the car reaches 75 miles per hour, let's say it stays at 75 miles per hour. Maybe you've set the cruise control to 75. Now the net force is back to zero because the speed is no longer changing. So to summarize, the net force was zero when the car was moving at a constant 60. It was non-zero when it sped up from 60 to 75. And then it was zero again when the car was moving at a constant 75 miles per hour. Now, what was the direction of the net force that caused the car to speed up? So looking back up here at our two cases for a moving object, if it sped up, then that means the net force and the direction of motion are the same. So let's say that the car was traveling to the east. Then the net force must have also been to the east. And again, I'm just focusing on one-dimensional motion here. We could go through a similar analysis for a car that's slowing down. So far with Newton's second law, we've basically been restating the first law in slightly different terms. But perhaps the most important part of Newton's second law is the way that we can use it to relate inertia and acceleration. So I want to talk about those concepts now. So mass, the mass of an object is the measure of its inertia. And inertia is the tendency of something to either stay at rest or stay moving. To put it another way, the more inertia something has, the harder it is to change its speed. So mass is a measure of an object's inertia. The more mass an object has, the more inertia it has. The less mass, the less inertia. And inertia is, if I can personify the object for a second, inertia is its unwillingness to change speed. So all of this can be summarized in a very simple relation, which looks like this. The acceleration, which recall is the change of speed, actually the rate of change of the speed, is equal to the net force. So you can see there's a direct proportion here. The bigger the net force, the bigger the acceleration. Divided by the mass. And this is an inverse relationship, since mass is in the denominator here. The larger the mass is, the smaller this fraction becomes, and therefore the smaller the acceleration will be. So this is Newton's second law written as a formula. If you've taken physics before, you've probably seen it written as F equals ma, which is the same formula. I've just rearranged it by solving for a. And the reason I like to do that is because, in my opinion, it makes it more clear that the amount of acceleration is proportional to the amount of net force and inversely proportional to the amount of mass, or the amount of inertia. So we'll be using these two laws in this week's activity, and you'll get more practice thinking about and understanding the second law formula. The one last thing I want to say about Newton's first and second laws is that the first law is really just a special case of the second law. And here's what I mean by that. The first law is the case of the second law when the net force is zero. So looking at the formula, we can see right away that if F net is zero, then the acceleration must be zero. Since F net's in the numerator, 0 divided by anything is 0. So acceleration must be 0. By the way, for those of you that are aware of the dangers of dividing by 0, don't worry. In all of the cases that we'll look at, the mass is going to be non-zero and positive. So another way of writing this could be, if the net force is 0, that implies that the acceleration must be 0. Bringing back the first law, we see that this new version is effectively the same thing we said originally. If the net force is 0, F net equals 0, then that object does not change speed. does not speed up or slow down, has no acceleration. Acceleration is 0. Okay, that's all I'm going to say about Newton's first and second laws. Now I'd like you to return to the Canvas assignment and answer the questions that are there. They will give you some additional practice thinking about these ideas. And you have an unlimited number of guesses on every question, so keep trying until you get them all.